Hello students and welcome to another video lecture on logic design. We were in the process of studying coordinate maps. You know that coordinate maps is a graphical technique used for reducing Boolean expressions. However, there are a few limitations of K-maps which make the need to find better techniques for reducing Boolean expressions. Firstly, K-maps are difficult to adapt for simplification of Boolean expressions having 5 or more variables. You have already seen how complicated the process is for plotting of a 5-variable K-map. Also, K-maps are heavily dependent on human abilities for simplification. It is thus a little difficult to program. Therefore, W.V. Quine and E.J. McCluskey developed a tabular method to simplify Boolean expressions. It is also called as the paper method or QM method. It is a systematic method for minimizing expressions of larger number of variables and is very easy to program as well. It is made up of two parts, finding prime implicants and finding essential prime implicants. Let us start with the first part, and that is the process of finding prime implicants. What are prime implicants? Prime implicants is nothing but an expression with the least number of literals which will easily represent all the terms given in an expression. Prime implicants are product terms which cannot be reduced by combining with any other product term. Also, in order to accurately use QM method, the function needs to be given in terms of minterms. So if you are given a question, find the prime implicants for the function summation m 1, 2, 3, 5, 6, 7, 8, 9, 12, 13 and 15. The first step is to order these minterms based on the number of ones present in their binary representation. So we'll start with index 0, where we look for minterms with 0 ones in their binary representation. Clearly, in the question, you can see that there are no minterms with 0 ones. So we start with index 1. Here we look for minterms which have a single one in their binary representation. We have minterm 1 with binary representation 0, 0, 0, 1. Minterm 2 with binary representation 0, 0, 1, 0. Minterm 8 with binary representation 1, 0, 0, 0. All these minterms have a single one in their binary representation, so they fall in one group. There are no more minterms which belong to this group. Now we go to index 2 and look for those minterms with 2 ones in their binary representation. We have minterm 3, minterm 5, minterm 6, minterm 9, minterm 12. And from the question, notice that there are no more minterms which belong to this group. So we start with index 3. Look for all those minterms with 3 ones in their binary representation. In this category, we will have minterm 13 and minterm 7. There are no more minterms in this group. Next, we start with index 4 and look for all those minterms with 4 ones in their binary representation. From the question, you can see that there is only one minterm which falls here, and that is 15, since it has 4 ones in its binary representation. You can continue this process for other indexes, but in our example, these are the only indexes available. The next step in QM method is to combine minterms from each group with the group exactly below it to form pairs. Since we have no minterms in index 0, we will start with index 1 and combine minterms from this group with minterms from index 2. For example, you can combine minterm 1 from index 1 group and minterm 3 from index 2 group. Notice that both these minterms differ in the second bit position from the LSB. So we can write this as a pair 1, 3 and the binary representation as 0, 0, dash 1, where the dash indicates the bit that is changing. Similarly, you can compare minterm 1 from index 1 and minterm 5 from index 2. Notice that minterms 1 and minterms 5 differ in the third bit position from the LSB. So we can write this as a pair 1, 5 and the binary representation can be 0, 0, 1, where the dash indicates the bit that is changing. Similarly, finding the other pairs from index 1 and index 2, we get 1, 9 represented as dash 0, 0, 1, 2, 3 represented as 0, 0, 1 dash, 2, 6 represented as 0 dash 1, 0, 8, 9 represented as 1, 0, 0 dash, 8, 12 represented as 1 dash 0, 0. Remember that the dash indicates the bit that is changing. Now we have exhausted the elements from index 1 and index 2 so that there are no more pairs to make. Now we combine minterms from index 2 with minterms from index 3. So we get the pairs 3, 7 and this is the binary representation. 5, 7, 6, 7, 9, 13, 12, 13 and 5, 13. We have exhausted the groups index 2 and index 3. Now we combine minterms from index 3 and index 4. So we get 7, 15, 13, 15 and this completes all the indexes and all the pairings. In the next step, we combine the pairs together to make quads. So we will combine from the first group of pairs with the second group of pairs so that two pairs combined will give you quads. Look at the pairs 1, 3 and 5, 7. Both of these differ in the third bit position from the LSB. So we can combine them as a quad 1, 3, 5, 7 and represent it as 0 dash dash 1. Similarly, we can combine 1, 5 with 9, 13 and represent that as dash dash 0, 1. In the same way, we find other quads and we get 2, 3, 6, 7 and this is the representation, 8, 9, 12, 13 and this is the representation. We have now exhausted the pairs from the first group and the second group. So now take the pairs from the second group and combine it with pairs from the third group. Doing this, we get 5, 7, 13, 15 and representation is dash 1 dash 1. Now if you look carefully, you cannot make any more quads. So now what do is try to combine the quads into octets, if possible. Looking clearly at all the quads, you can see that none of the quads can be combined since all of them are unique. So the process stops. Now for sake of clarity, I will display the previous slide again without all the markings. The biggest grouping that we have here are quads, which is a combination of 4 minterms. So we check each pair if it is contained in any of the quads. If a pair is contained in any quad, we will mark it with a small arrow. Take for example the pair 1, 3. It is contained in the quad 1, 3, 5, 7. So I will mark 1, 3 as present with an arrow. Next we check 1, 5. This is also contained in a quad 1, 5, 9, 13. So we mark it with an arrow. Check 1, 9. 1, 9 is also present in the quad, so we mark it with an arrow. Similarly 2, 3 is also present in the quad 2, 3, 6, 7. We mark it. Check 2, 6. This is also present in a quad. 8, 9 is also present as a pair in some quad. 3, 7, 8, 12, 3, 7, 5, 7, 6, 7, 9, 13, 12, 13, 5, 13 are all present in the quads. So is 7, 15 and 13, 15. In other words, all the pairs are contained in the quads that we have made. We don't have any octets in this example, so we can't check for quads being in a bigger grouping. So all these quads are now called as prime implicants. Rewriting all the quads on a new slide, we conclude this problem by assigning variables to all the quads. If this column is A and this column represents B, this column represents C and this column represents D. So 1, 3, 5, 7 represented as 0 dash 1 is A bar D. Remember, they are min terms. 1, 5, 9, 13 represented as dash 0, 1 is C bar D. 2, 3, 6, 7 represented as 0 dash 1 dash is A bar C. 8, 9, 12, 13 is A C bar. 5, 7, 13, 15 is BD. Remember, these are all min terms, so they can be represented in the form of an SOP expression, which is this. That's all for now. Step 2 of finding essential prime implicants will be explained in another video. Connect to the classroom for more videos and study material.